So let's start talking about double integrals. Up until now, everything in this class that we've done has been concerned with derivatives, or almost everything. We briefly mentioned integrals when we talked about integrals of vector functions. Other than that, it's all been about derivatives. Specifically, we've been generalizing the derivative concepts from Math 10a to functions of multiple variables. Well, at this point in the class, we start generalizing the content of Math 10b to functions of multiple variables. So instead of generalizing derivative concepts to more than one variable, we'll be generalizing integral concepts to more than one variable. As you can imagine, this is a super useful and applied topic. Pretty much everything in this class, actually, has application, and integrals are a major application in this class. I probably cannot overstate the applications, but today, for the most part, I'm just going to be talking about concepts. We'll get to some applications soon enough. So let's get started. And because, as I said, I'm going to be generalizing Math 10b material, let me start by reviewing some Math 10b material. So specifically, I want to review the concepts of signed area and Riemann sums from Math 10b. These were two core fundamental concepts that you learned about in Math 10b, and let me remind you of how they went. So suppose we have a function of one variable f of x. Suppose that f is defined on some interval ab. So if this is a and this is b, maybe the graph of f looks like that. Then we can define the definite integral of f. And there's actually three equivalent ways that it can be defined. The first way that it was defined was in terms of signed area. So the signed area is the area that's beneath the curve but above the x-axis. That is this area minus the area that is above the curve but below the x-axis. That is this area. So if I call that first area, how about capital A? And I call that second area, how about capital B? Then the definite integral of little f from little a to little b will be equal to capital A, that's positive area, minus b, because that's negative signed area. So that was the first definition that you probably saw in Math 10b of a definite integral. Shortly thereafter, you learned a second equivalent definition of a definite integral in terms of Riemann sums. So here's the equivalent way to define the definite integral. Let me again suppose that we're looking at some function f defined on some interval a to b. You can split the interval a to b up into subintervals. Let me split it into n equal subintervals. And let me label the endpoints of those subintervals, starting with a, which I'll call x0. The next endpoint of a subinterval I'll call x1. The next one I'll call x2, all the way up to x sub n minus 1, and then b, which I'll call x sub n. Okay. Let's suppose that delta x is the width of each of those subintervals. And now I'm going to pick a point from each subinterval. Let's call it x sub I star, if it's chosen from the ith subinterval. X sub I star is what's called a sample point. It can be the left endpoint, it can be the right endpoint, it could be the midpoint. It doesn't actually matter. So here, let's say x1 star is right there in the first subinterval. Maybe x2 star is right there in the second interval. Let's say xn star is right there in the nth subinterval. Having chosen your sample points, you can create these rectangles whose heights are given by the value of the function at the sample point. So let's see, the height of the function at the first sample point will be right there. So that's going to be the height of my first rectangle. The value of the function at that second sample point is right there. So that's going to be my second subrectangle, or second rectangle. The height of the function at the nth sample point is right there. Okay, so we now have n rectangles, and when you add up the area of the n rectangles, it should approximate the area underneath the curve. Right? Like this area plus the area of this rectangle plus the area of that one plus the other ones that I didn't draw should be close to the area underneath the curve. We would call the sum of the areas of those rectangles a Riemann sum. So here's a Riemann sum. It would be, let's see, the area of the first rectangle, which was f of x1 star delta x, plus the area of the second rectangle, which is f of x2 star delta x. Plus all the way up to the nth rectangle, which is f of x n star delta x. And you can write that more compactly using summation notation as the sum from I equals 1 to n of f of x sub I star delta x. So that's a Riemann sum, and as I said, it approximates the area underneath the curve. But what if we took, yeah? Yeah. Here? Oh, right there. Yeah, delta x. Thank you. What if we take an increasing number of subintervals? So if we take an increasing number of subintervals, that makes them smaller, or skinnier rather, but we get more of them. The more subintervals that we take, the better our approximation to the true area underneath the curve will be. In the limit that the number of subintervals go to infinity, we get the exact area underneath the curve. In other words, the definite integral of f. That is our second and equivalent definition of a definite integral. Okay, it's the limit of the Riemann sum. There's actually a third equivalent definition of a definite integral using the fundamental theorem of calculus. I didn't write it here, though, but starting today, we will see 3 equivalent ways to calculate integrals of functions of 2 variables. First, however, I need to introduce some notation and terminology. So we've already seen that intervals can be written with closed brackets, like the interval from A to B. Equivalently, you can write them with so-called set builder notation. So another way to write the interval from A to B is as follows. It's the set of x such that A is less than or equal to x is less than or equal to b. So there's a few symbols in this expression that have English word translations. And when you see the symbol in your mind, you should think of the English word translation of that symbol. The first one is the curly brackets or braces right there. So when you see those, you should think the set of. So this set is the set of x, and then the colon also has an English word translation. So when you see the colon, who knows what the colon stands for? There's a better phrase for it. Yeah, the colon has an English word translation or English phrase translation. This symbol stands for the phrase such that. When you see the colon, it means such that. Okay, so that's another way that you can describe sets, and it's useful, and we'll occasionally make use of it. We'll occasionally make reference to the set of all real numbers. There's more than one way to notate the set of all real numbers. One common way is with this sort of weird-looking R. So this is called a blackboard bold R. It's a special kind of bold. LaTeX, by the way, has a version of this for every letter of the alphabet. But anyway, when we write it, it means the set of all real numbers, and you can also notate it using interval notation as the open interval from negative infinity to positive infinity. If you have two sets, then you can define their so-called product. And don't be confused, by the way, with multiplication. By product, what I mean is the following. The product of two sets A and B, written A, then with a multiplication times symbol, and then B, it's the set of coordinate pairs, x, comma, y, where x is in A and y is in B. Okay, so in set builder notation, I could write that as the product of A with B is the set of pairs x, comma, y, where x is in A and y is in B. If you take the product of a set with itself, say A cross A, you can also denote that with a little power, a superscript 2. Okay, so A cross A is the same as A to the second power, if you will. So in particular, we can describe the xy plane using this notation. Right? The xy plane, wait, but that's the set of all pairs xy, where x is a real number and y is a real number. In other words, that's R cross R, which may also be denoted R2. So R2 is the Cartesian plane, is the xy plane, is the Euclidean plane. All those names mean the same thing, the familiar xy plane. Finally, we're going to be talking about rectangles in the xy plane. So a rectangle is a set of the following form. It's of the form r equals some interval times, or product with some other interval. So let me draw you what this rectangle AB cross CD would look like. Let's say this is the rectangle in question. Then the x values in the rectangle will extend from A to B, and the y values in the rectangle will extend from C to D. Okay. So now that we've got this out of the way, I can start to define the main topic, which is a double integral. Oh, wait. So first, let's suppose that we have some rectangle R in the xy plane, like the rectangle that I just drew, actually. Okay, so here's some rectangle. And suppose that we have a function of two variables, f of x, y, which is defined on this rectangle. So f takes values in this rectangle and spits out some number. And in fact, let's suppose for the moment that f only spits out positive numbers. I'll get to negatives shortly, but for now, let's suppose f is a positive function defined on this rectangle. Define the double integral of the function f over the rectangle R to be the volume beneath the graph of f, and denote it by this double integral symbol, which is literally two integral symbols, a subscript indicating the rectangle that we are integrating over, followed by f of xy, which is your integrand. This is the integrand. Followed by dA, which is your differential area element. It's like the 2D version of dx. In fact, we might occasionally write dx dy instead of dA. So same thing, dA or dx dy, either one works. Either one will work. And sometimes we actually suppress the of xy notation and just write f when the context is clear. So all three of these ways will work, and they all mean the same thing. Let me try and draw what I'm talking about here. So let's see, let's suppose that here's my rectangle R. Okay. So this is R. And f is defined on R. So above each point in R, f has some value. So its graph lives somewhere on top of R. Let's say something like this. Okay, so let's say that that curvy surface is the graph of f. Then the volume beneath that surface, but above the xy plane, is the double integral. Okay? So whatever the volume here is, that's what we mean by the double integral of f. So there's your first definition of a double integral. Like I said, I'm going to show you 3 equivalent ways of describing it. This is the first way. Let's practice using this first notion of a double integral. Suppose f of xy is equal to 1 minus x, and that this is defined on the unit square, 0, 1 squared. Remember, that's equal to 0, 1 cross 0, 1. And let's compute the integral of f over r. Or, sorry, the integral of f over the unit square. And sketch it too. So let me sketch it first, actually. Let's see, the unit square is, this is 1, and this is 1. So there's the unit square. So this is the domain. The function will be plotted on the z-axis, and it's equal to 1 minus x. So it doesn't actually depend on y. You can plot some points if you want. Maybe you already know what it looks like. I'll just show you what the result is. So let's see. It's equal to 1 at 0, and then it goes down with slope 1 in the x direction. Can someone tell me what shape describes the volume which is equal to the double integral of f? The double integral of f is equal to the volume of some shape. Describe that shape. What's it look like? Nice. Shoot, yeah, it's pretty descriptive. Yeah, that's right. You could also call it a wedge, but that's actually more accurate. So it's a wedge. See, here's a picture of it. Yeah. It's this wedge right here. And to find its volume, you know what? Here's a useful formula, which we're actually going to prove, I think, next section. Let's say you have some region with area B. And you make a cylinder out of it, meaning extend it straight in one direction, perpendicular to it, a distance h. Then the resulting solid has volume given by B times H. So that actually applies to the wedge that we're looking at in this example. If I treat, let's see, this is the face. It's a triangle. So the area of this triangle is 1/2 the base times the height. Base and the height are both 1. You just get 1/2. And the depth of this shape, or the height, if you're using this h, is also 1. So the volume which is the same as the double integral, well, it'll be 1 times 1/2, which is 1/2. So that's the volume of the wedge. Okay, so we're already doing double integrals. Of course, in this case, it was pretty easy because, well, we had an easy geometric formula for it. So I mentioned that I was only doing the definition for positive functions for the moment. So now let me generalize to negative functions. Suppose that we have a function which is not necessarily positive. How then can we define the double integral? Well, we can extend the definition analogously to how it was done back in Math 10b. If you recall, they extended the notion of a definite integral to functions of one variable in Math 10b by introducing the concept of signed area. So in our case, let's introduce the concept of signed volume, wherein volume that lies below the xy plane is counted as its negative. Okay, so we can extend the definition of a double integral to functions which are not always positive by defining the double integral of f over r dA to be the signed volume underneath the graph of f, defined by the following. The double integral is equal to the volume which is below the positive values of f and above the xy plane minus the volume which is above the negative values of f and below the xy plane. To show you a quick example of this concept, let's compute the double integral of 1 minus x, same integrand as in the last example, by the way, but now over 0, 2 cross 0, 1. In fact, let's look at the Math 3D graph of this, which is right there. Okay. So there's the graph of 1 minus x over the interval 0, 2 cross 0, 1. Okay, so let's see if I can draw this. First, the domain is this rectangle right here. And now I want to shade in the region which is below the graph when it's positive, but above the graph when it's negative. All right, so let's see. All right, I think I can see what to shade in. So we're going to have positive volume right here, because this is above the xy plane. And we're going to have negative volume right here. Because that part is below the xy plane. what are the volumes of those two pieces? By the way, volume is always positive. Signed volume can be negative or positive or zero. What are the volumes of those two pieces? What do you think, Brian? Oh, yeah, right, yeah. Because the first piece is just the previous example. Then the piece that lies below the x-axis is actually looks just like the first piece, okay? So they're both 1/2. Both have volume 1/2. That is, I said volume, I didn't say sign volume. Both have volume 1/2. Now the double integral is the sign volume. So what's that? So the answer to the question, the double integral over 0, 2 cross 0, 1 of 1 minus x dA, it'll be what? What will it be? Good, very good, yes, because it's 1/2 minus 1/2, which is 0. Cool, so that's the concept of sign volume. Okay, so we now have our first definition of the double integral. Let me now give you a second definition of the double integral, because not every shape has a ready-made geometric formula for us to use. So, just like we did back in 10b, we have an equivalent definition of the integral in terms of Riemann sums. So let me attempt to define a Riemann sum for a double integral now. And this part's a little bit technical, so bear with me. Suppose we are again looking at some rectangle R in the xy plane. So let's say there's our rectangle R, and it's equal to AB cross CD. Remember how in the one variable case we chopped up the interval into subintervals? Well, that's what I'm going to do here to both AB and to CD. So let me chop AB into a bunch of subintervals. Say, yeah. 1, 2, 3. Let me chop CD into some subintervals. Okay, so let's say I split AB into n equal subintervals. Each one then would be of width delta x. Let's say I chopped CD into m equal subintervals, and let's call the width of each of those delta y. Let me label the ith subrectangle as R. Sorry, let me say that again. Let me label the ijth subrectangle as R sub ij. So the first one right here, that will be R11. The second one right here, that will be R21. Let's look at another one. How about, say, like this one right here? That would be, what would that That would be R1, 3. What would the bottom right corner be? This one right here. What, R4, 5? So each one of those subrectangles has width delta x and height delta y. Hence, the area of each one is delta x delta y. And we sometimes call that delta A. Next comes the part where we choose the sample points. So let's choose a sample point from each subrectangle. We'll call it x sub ij star, y sub ij star. So for example, in the first subrectangle, let's choose some sample point. It doesn't matter where in the subrectangle you choose it. It could be the midpoint, it could be the upper left, the lower left, upper right, doesn't matter. Somewhere in that subrectangle, we're choosing the point x11 star, y11 star. In the next subrectangle, somewhere, maybe how about the upper left, we'd be choosing the point x21 star, y21 star. Somewhere in the R13 rectangle, we'd be choosing x sub 13 star, y sub 13 star. So you want to do that for each subrectangle. Then you've got a bunch of sample points. And having done so, you can define the corresponding Riemann sum. So here's what it is. It's the sum from I equals 1 to m and j equals 1 to m of the function value at the ijth sample point times the area of the subrectangle. So in other words, you just sum over all the subrectangles. Over this one, plus this, plus this one, 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 over all of them. Their area times the function value evaluated at the sample point. So each one of these terms is going to be the volume of a box with width delta x, depth delta y, and height f of x sub ij star, y sub ij star. All right, so the volume of this box right here is exactly what we're summing up. So when you sum over all the subrectangles, it's like you're summing up the volumes of a bunch of boxes. Here's one. Here, by the way, I put here a couple pictures, one from our textbook and another from another textbook. I like the picture from the other textbook better, so I'm going to use theirs. I didn't try to draw this myself because this is a hard thing to draw. So what we are adding up with this Riemann sum is a bunch of these rectangular box volumes. All right, one over each subrectangle. Notice that according to this picture, this is going to be close to the volume underneath the surface. That is to say, it's going to be close to the double integral. Like, it looks like, let me zoom in here for a second, there might be a little bit of error. Like, maybe this, there's a little bit of error right here, but other than that, we're capturing most of the volume with this box right here. And similarly, on the next piece, yeah, there's a little bit of error right on top, but other than that, we're capturing most of the volume. And you can imagine that in the limit that you take a greater number of subrectangles, you get more and more of these, can't draw this, you get more and more of these skinny little rectangular boxes underneath the surface of the graph of f, that the volume that corresponds to the sum will be closer to the actual true volume underneath the graph of f, just like happened in the one variable case. So that's the content of our second definition of the double integral of f. So our second and equivalent to the first definition of the double integral of f will be as the limit as the number of subrectangles goes to infinity of the Riemann sum. And again, hopefully you can see that as you let the number of subrectangles get really large, this is hopefully a very good approximation to the actual true volume underneath the graph.